in this scenario, the name of your company is Chemitech, and you're wanting to determine which filtration assembly method is the most efficient as measured by units produced over a given time period. So below are the numbers of the units assembled by method over a time period. This might be hours and days or something like that, but it doesn't really matter. So you have method A, method B, method C, 58. Here's all the different observations. The second output, or table 2, is the actual output from an Anova analysis from a typical software package. And in this situation, we're using Excel StatPack. And a couple areas that are happening here, the primary breakdown is going to be here, your summary values. And these are the means for each one of the three methods, and we're going to be doing a means analysis to figure out which one potentially is not like the other, or which one is the most efficient as measured by units produced over time. The other area of the chart, and this is kind of more or less the meat of the chart in the initial analysis, is we're going to look at the F values. Here's the critical value, here's the statistic test value, and then the p-value, and then we're also going to be working a little bit with the MSE. So in this enhanced scenario, you're the production supervisor, and you need to make a recommendation to the plant manager as to which process to use going forward. The plant manager, as are most business folks these days, or business people these days, have a strong data savvy approach to their decision makings, cross-cut that with experience and then their gut feel, and they make a decision based upon the evidence at hand. So thus, any recommendation you make needs to be clear and concise, evidence-based, and then results using the language of statistics and analytics. So the technique, more or less taking it from the top, is we're going to do an Anova analysis. So this is the Anova checklist. And the first, here are the series of questions that you're going to be asking yourself to more or less investigate this data set and determine which of the three methods is most efficient. And one of the big reasons you would do that, of course, is that the more units you produce over a given fixed asset or fixed cost, the lower your cost per unit is going to be. So an appropriate research question in this case, that was the purpose and the problem. The appropriate research question is which method has the highest production volume. For interrogating this analysis, the null and an HO and an HA. HO is you set mu sub 1. I'm going to rename these mu sub A, mu sub B, and mu sub C for each of the three methods. And you set them all equal to each other. And then you set them not equal to each other. And what you're going to do is you're going to take a look at HO, and if at least one of these is not like the other, that's a little bit of a Schulteism, but if at least one of these is not like the other, then you would reject null and move on to the alternate and do some additional testing that we'll talk about as necessary. So you're going to conduct an Anova analysis. That's a type of testing. And the variables, you're going to have two variables. You're going to have production volume, and then you're going to have the method. So those are the two variables that you're including in your model. As far as, and you're going to run this at a sig.05. 95% confidence level, p less than 0.05. And as far as exposure to invalidity and reliability, one of the most often addressed or used as far as invalidity goes is take a look at that sample size. And here you can see the sample size for each production method is about 5, so you get 15 data points. So this is a little soft as far as sample size goes. So that might be one area where there'd be some invalidity. The other one that you might look at is time of day and day of week, because the number of units might change as you are on a Monday or a Friday or in the afternoon or morning. So you'd have to control for that. So that might be another source of invalidity that you would need to address. But let's continue on with the analysis. Assuming that we have addressed any or discussed appropriately any exposure and invalidity and reliability, and the ability to repeat the test over and over again and get the same results. So now, the next part of this is you want to actually go in and begin testing the hypotheses. Mu sub A, mu sub B, mu sub C are all the same. And to do that, first thing we want to look at is what is the test model critical value. So we're going to create a test model that looks like this. And this is on an F basis. So we're going to have an F critical value. All right. And so the first one you want to take a look at, or first value you want to take a look at, is this critical value. Let me zoom in on that a little bit. Here's the F critical value. So as you can see, this is 3.885. So I'm going to just round that to 3.9. as the critical value. The test statistic, keeping moving along or working with the actual output, is you have, here's your test statistic. It is the F value, and it's 9.17. So I'm going to round that to 9.2. And that's all we really need to pull right now from the output, on this output here. And so now we're going to create our test model at P.05. And so you're going to, as normal, you're going to label this as the do not reject HO, meaning that they're all the values or all the means are the same. And then you're going to have this reject zone where you're going to reject the HO, or at least one of those is not like the other. And if you take your test statistic, which was 9.2, run it against this model, you can see that this was your test statistic, which was 3.9. So clearly you're out here somewhere. So you're in the zone where you are rejecting the null hypothesis. Let's verify that with the test statistic p-value. Zoom in on this one more time. You can see here that the p-value is 0.00318, and I'm just going to round that to 0.0038 or 0.0038. So p is equal to 0.0038, which clearly is less than 0.05, which is the standard you set up for the testing. Less than 0.05, so you first verified through the critical value method that you would reject. On the p-value technique, you're also rejecting because 0.038 is way less than 0.05. So you would clearly, in this situation, there would be very sufficient evidence to reject the null. And going back to the null hypothesis itself, you're going to reject these, so at least one of these is not like the other, or you would be rejecting mu sub A is equal to mu sub B is equal to mu sub C. And you come back and you'd actually accept the HA at that point. Now, setting the original analysis aside, the next piece we want to do is we want to determine where this difference is occurring between the three sample means. And so what you do there is a very kind of a straightforward analysis. It's a, if you will, a mini critical value analysis in which we established or which we will establish an LSD, and if that value that we're going to understand for the difference is greater than this LSD value, then we would reject. And we'll fill in that blank in a second. So the first thing you need to do is come in here and decide how you will go about interrogating that, which is with this LSD value. So we're going to create like I said, a pseudo-critical value out of the LSD. And this is a confidence interval technique. But you can see here, this is from 13.17, chapter 13, equation number 17. And if any of these equations are required on an exam so I'll give those to you, obviously. So your equation becomes LSD is equal to T sub alpha over 2, because all confidence interval analyses are a two-tail, times your MSE times 1 over n sub 1 or n sub I plus 1 over n sub j. In this situation, the sample sizes are all the same, 5. So you can use this same LSD for all the matchings that you're going to analyze to determine where the difference would lie. Now, let's fill in a few more pieces of information here. The MSE, where we get the MSE from, is, let's fill these in. The MSE, we get that from our output. And we can see that our MSE, we're going to home in on this number right here, is 28.3. So we fill in 28.3. Then we go 1 over 5, which was the sample size for each of the, or at least for a specific pairing. And we'll talk about those pairings in a second, over 1 over 5. Now the only thing missing here is this T sub alpha over 2. And we're going to get that from is going to go back to our handy dandy T table, and we're going to, this is a two-tail, so we're going to be in this 0.025 column, but we need to figure out what our degrees of freedom are. And as a little bit of a side analysis, degrees of freedom is the total number of samples minus the number of columns, or the number of categories. So as you're going to see here, there's the total number of samples is 15. There are 3 methods or 3 columns. So we're going to get a degrees of freedom of 15 minus 3, or 12. Back here to our T table. And like we've done hopefully you've done many times at this point, 0.025 and 12, 2.179. You run that out, or run it into your calculator, and you're going to get a value of 7.34. So if any of these, so now what this says is if any of these LSDs are greater than 7.34, or not the LSDs, but the difference between the two means as we compare each of these matchings, and again we'll talk about that in a couple seconds here. If any of those matching is greater than 7.34, you will reject that individual matching, and you would claim that they are not the same. The 3 matchings I'm going to take a look at is x bar sub A minus x bar sub B. And these are absolute values, so it really doesn't matter what order you put these in. X bar sub B minus x bar sub C. And then we're going to look at x bar sub C minus x bar sub A. Going back to our output table, as we know that our x bar in Excel they call it the average instead of the mean, but it doesn't really matter. So x bar sub A minus x bar sub B, 62 minus 66. absolute value is equal to 4. Is 4 greater than 7.34? No, so these are the same. Or not significant evidence to suggest that there is a difference. Let's take B minus C. B is going to be 66, C is 52. So now we come in here and we go is equal to 66 minus 52, absolute value, and that's going to be equal to 14. In that case, 14 is greater than 7.34, so you would conclude that there is a difference, or there is a significant difference at p dot 05 for the matching of x bar sub a minus x bar sub c. Finishing up this analysis, and I'll zoom back out here in a second, is then, but you still have to take a look at the matching between c and a. So x bar sub c is 52. X bar sub a is 62. And that's equal to 10 on an absolute value basis. So there's a difference there as well. So the true culprit here, or the difference that is occurring that you're understanding, is that method C is the odd man out here, if you will, or odd method out. And let me zoom back out just a little bit. And so method A, method B, method C, and 56, 66, 62. So clearly C is one of those methods that you would clearly not further consider. The only issue is that 62 and 66 statistically, using inferential statistics, are the same at p dot 05. So now what do you do? So here's your business recommendation that you would go about. You say do not select method C. Obviously that one would not work for you because it's the least efficient as measured by the number of units produced over time. But you'd have to come in here and somehow you still have to make a recommendation to the plant manager, and so you'd come up with another criteria. And a typical criteria there, and you can think outside the box as much as you want here, but you might take a look at the cost for the raw materials to decide between A and B. And so you'd have to go in and do a little more analysis to determine if the raw materials were different between A and B, by which to make a sound business recommendation. That's how you'd go about analyzing an Anova, where you have multiple means. And if you have any questions, let me know, and I'd be happy to address those for you. Thank you.